Non mi ha toccato te. No? Okay. So, okay, let's try to summarize the logic of past lectures. Okay. So we have seen that we have this conservation law. Okay, in 2 dimension. Okay, and that if which is the 1 + 1 dimensional anomaly, chiral anomaly. Okay, what is special about this is that if you integrate it out into space, okay, if you integrate this into space on two sides, this has to do with integer numbers, right? Because this become the change of charge between different branches of the two branches of the Fermi of the Fermi of the fermion, okay, and an adiabatic change, okay, and this is then related to an integer, to n, because this quantity, when it is properly integrated, okay, it's integrated in a compact space, this quantity is an integer, so, okay, is a topological invariant. And after all, everything boils down to the fact that you have a large gauge transformation, okay? So this is a large gauge transformation. It is possible that this is an integer because of the large gauge transformation that you do when you join the two parts of a cylinder to make a torus, or when you join the two parts of the of the of the sphere to join to make a sphere to make a compact. Okay, so large gauge transformations which have to do with the compact space and compact group U1, okay? And why should I care about a compact gauge group? Compact gauge group? Well, because in quantum mechanics, the gauge field appears to the exponent, okay? Appear to the exponent. So this can be sometimes, okay? So that's the end of the story, okay? So mathematically, this is the point, okay? This is a very special thing in which you can have a adiabatic process in which you realize a large gauge transformation, then the Hamiltonian of your system, it corresponds to also to large gauge, also correspond to a flux insertion, quantum of flux, okay, quantum of flux, phi naught. And you can say that because there is a large gauge transformation, the Hamiltonian returns to itself. Okay? By large gauge transformation. Okay? So there's a special property about these anomalies that are related to integers. Okay? And also, because of this, they are independent. The effect that you are describing is independent of smooth deformations. Smooth deformations. So if you have a physical system which is associated to this quantity, then you find a characterization of a system which is independent of smooth deformations. Smooth deformation of what? Well, smooth deformation of the external background, okay? For example, we discussed the quantum Hall effect, and we found that indeed this same number is equal to the Hall conductivity. And that the spectral flow that is realized by this current is equivalent to the Hall current, okay? So finally, if you have this configuration of the Hall effect and you put this flux dependent of time, if you change this from 0 to phi naught, then you move all the electrons like this, and eventually you move one charges from here to here, which is the Hall current, okay? And so the Hall current is, okay, with the same coefficient, okay? This is the same equation, only that this is 1/2 of that, okay? So this is an integrated form of okay, with sigma okay. So we have a characterization of this system, for example, on also other system, which is independent of smooth deformations. So the smooth deformations of the external background, okay, because you don't expect that in an experiment you will have a precision, for example, of the gauge field or fluctuations to the order of 10 to the minus 9, okay. It's impossible to realize such a precision in a system. You will have fluctuation, thermal fluctuations, impurities, deformation. Hamiltonian can be, the lattice can have impurities, can have dislocations. All sort of phenomena can take place at this scale of precision, okay? But you discover that this fact is independent all of this because the property of invariance under smooth deformations. Okay, so the general philosophy is that you have topological phase of matter which are characterized by these quantities like the Hall conductivity. The ground state is characterized by this quantity which are these numbers which are independent of smooth deformation. So this is a kind of universality, idea of universality. In critical phenomena, you have, so, so, okay, so of the gauge field A mu, or also change of the Hamiltonian. The Hamiltonian can have some microscopic Hamiltonian can have all kinds of accidents, okay? I don't know. An electron that, this morning wakes up a bit strange and doesn't want to follow the flows. So some psychology of fermions, I don't know, some ant going around the lab nearby and destroy some mouse that want to grasp a cable, I don't know, in the lab or anything, okay? So this is independent invariance under smooth deformations that characterize the topological phase of matter. So you may be aware of that since many years that you have topological excitation. So you have a normal ground, you have a normal system, but somehow there are excitation like vortices which are characterized by topological numbers. For example, the winding, no? The winding of the phase in a superconductor or a superfluid. This is a topological excitation. Okay, this is instead is a topological property of the ground state. Topological property of the ground state, not of excitation. Of course, also excitation then are subjected to a series of properties following from this topological property of the ground state. Okay? So that's the logic. And then, so the connection between physics and mathematics is that you have a system which is in a certain phase and has some properties that, in general, a massive phase, some properties that remain invariant if you deform smoothly the Hamiltonian without closing the gap. Of course, if you close the gap, then you go to another phase. But in that phase, this property, for example, that the Hall conductivity is 1 or 2, doesn't change under smooth deformation of the Hamiltonian and the smooth deformation of your system and the background and these type of things. Okay, that's the logic. Okay, do you have question about this logic, philosophy, or? That was the logic. So last time we showed that that there is okay, that in fact you can represent a spectral flow of a fermion in this situation because basically the you have a gap here in the bulk. So if you do things smoothly and slowly, adiabatically, you cannot excite here electrons. And then in fact at the end there is there are on the boundary there are this massless fermion excitation, and so you realize the the spectral flow from one band to another as in the 1+1 dimensional fermion. Okay, that was the idea. Okay. I have to say that there is not only this we show, okay, that there is a smooth deformation of the gauge field is this, okay, and doesn't change the result for the Hall current. There is also a proof based on smooth deformation Hamiltonian because there are a series of papers by Towles and collaborator they show that indeed in this system you can compute the Berry phase and find that the Berry phase of this Hilbert space is again related to the Hall current. So there is both a background property with respect to change of the background and also a property with respect to change of the parameters of the Hamiltonian. Okay. Okay. So the fact that this is this quantity has a topological origin, you can see both from argument of anomaly and on argument on the Berry phase. Okay, and okay, now next subject. Do you have questions about this? Did you get to the point? No questions. That was basically my point so far, right? Okay. Well, at this point we are going to go one step further and discuss not this was the integral effect. Okay. So and now we discuss the fractional. Okay, so what's the point? Well, after a few years that they discovered that there are these integer values of the Hall current, there are also fractional values. So there are so sigma h is There are a number of fractional values, especially these numbers which are 1 over odd 1 over odd values, which is called Laughlin states. Okay. Okay. What's the point? The point is that in case of this gap here and this property which was kind of important in this argument was based on the fact that you feel completely Landau level. Okay. So you had this idea that on this system you have radial wave function which are all like this, okay? And then on each of them you have a fermion, so it's fully packed, okay? Fully packed. But if you feel, if you put 1/3, it means that you can see that in this quantum mechanical system you put 1/3 of the electron, you feel 1/3 of the possible states. So from a point of view, one particle states, you basically put an electron here, an electron here, an electron here, okay? 1 out of 3, and there are many possibilities because they're all degenerate. So this is for this value 1/3 is a filling fraction. 1/3 means that you put on average 1 electron every three possible one particle states. So this is a very degenerate case. So how is possible that the same physics is observed like for a fully packed state, okay? Fully occupied state. Well, the idea, so is there a microscopic picture for this? No, no, okay. No, because it's a non-perturbative phenomenon. Maybe you know that when you have a non-degenerate ground state for free fermions, then you add some interactions. You can treat them perturbatively or effectively, but it's very important that the starting point of free electrons is non-degenerate. Okay, if you have a starting point of free fermions which is degenerate, to get a gap, because you want to get a gap, is non-perturbative phenomena. Okay, something that you cannot reach by assuming that the interaction among the electrons is small. So it's a kind of a miracle. Okay, and so at this point you cannot get so far nobody was able to describe it in terms of microscopic physics. Okay, so you have to rely on effective theories, effective formulation. Okay, effective field theories. So you assume that you have this gap due to Coulomb interaction, and then you proceed by developing ideas of symmetry, of topology, like you do in critical phenomena. Okay, you assume that you have a low energy physics. So first of all, you assume that you have a gap, and then around this gap you will have some low energy physics that you can describe in some effective way. So we are assuming that somehow in this case there is a gap due to the Coulomb repulsion among the electrons, and so also in this case they repel each other. Okay, in very peculiar way that I will discuss more. They repel each other, so there is still a gap, and there are edge excitations, massless edge excitation as before. Okay? That's the idea. And Laughlin also proposed a wave function for this to exemplify this possibility, okay, and some other tricks that I'm not going to discuss. But the idea, the basic physical idea is that of the incompressible fluid. if you have a completely filled Landau level, the density as a function of the radius, okay, here radial direction, the radius is just a form like this, okay? Because you have this one particle states that are kind of little Gaussian around every synchrotron orbit. Okay, when you pack all of them, you make something which is constant in the interior. So a constant density here is characteristic of a fluid. Okay. So in the interior, this is like a droplet of liquid, okay? Droplet of liquid. But there are no density fluctuations. You cannot do a density fluctuation here because this would require to make a jump of an electron to the next Landau level, which is very big, is forbidden. So it's a fluid without density fluctuations. So it's an incompressible fluid. Okay? And so the density rho zero is in this unit. If I put b equal to 2 and l equal to 1 and many other coefficient fixed, is no. Okay? This constant. Okay. So the idea is that you have even in the fractional case you have an incompressible fluid. At this point, the electrons are sparse, but somehow they manage to get a gap, and so it's still a fluid. Okay, is it possible to have such a physical situation? Yes, it is possible, because in general, when you have a Coulomb interaction and electrons, and there are not so many electrons, they form as a regular lattice. Okay, because Coulomb interaction is long range, they form a kind of regular lattice, which often is a hexagonal lattice called the Wigner lattice. But when you pack the electron together to a sufficient density, then it is possible to go into this fluid phase in which the Coulomb interaction is actually screened. Okay, so it becomes a short-range interaction dynamically, and with a short range, if you have balls with a short range interaction, is like a liquid. Okay, so you can have a constant density ground state. Okay, like balls in a I don't know, like popcorn. They have a short range interaction. But, okay. Okay, so what is the idea? The idea is that if you have a 1/3 density, then this is 1, then you have a incompressible fluid like this, 1/3. Okay, this is ideas by Laughlin. Okay, physical idea, and so then we can also say, oh, I have a gap. A gap will be related to the Coulomb interaction this time, not to the to the to the gap between Landau levels. Okay, so the gap will be of the order of E square over R, and so E square over length of magnetic length, which is the only length is possible in the system. That means that forces are screened at the level of the magnetic length. Okay, so that then gives remembering that L square is okay. Is then it gives you something which is proportional to square root of b. Okay, we have such a thing. Okay, and then you say, okay, what is an excitation in this fluid? Well, let's think in the analogy with the integer case. you remove an electron from here, and so you make a small hole here. And this small hole, because you remove the electron, this small hole has a gap and has charge Q equal to 1 with respect to the ground state, because you remove one electron. Okay? Okay, so if you do now a similar hole in this one-third fluid, the size of the hole is the same because it's associated to the fact that the length of microscopic physics is still the magnetic length, okay, the size. And so the charge that you create with this is one-third. If this is one-third, it's one-third. So you have excitation which are called quasi-hole with fractional charge. Okay? Yes? Yes? No, it's not rotational invariant. It's a hole in this. It's an abuse of notation, yes. So the hole has to be seen here, okay? Okay? But what counts is the area of the hole, okay? The area of the hole is L square, or pi L square, okay? And so you make a smaller hole and a fractional charge, okay? Then there is this fractional charge, okay? That's the first idea. And then there is a second idea that it has a fractional statistics. Meaning that if you take two such holes, quasi-holes, and you bring one around the other, they are neither boson nor fermion, but they acquire a phase which is one-third of the statistical phase. So the wave function for position eta 1 and eta 2, like these are eta is complex number, which is okay. Let me call it A and B, okay? Otherwise we make confusion. Now let's call it eta and eta prime, okay? And eta is eta 1 plus I eta 2 is a complex coordinate in the plane. The wave function is analytic function. We remember, no, there is a prefactor which was some exponential, then there was an analytic function, and this has a factor eta 1 minus eta prime to the one-third, so that if you rotate one around another, you get a phase okay? And then, of course, there are all the electrons coordinates here, like Z1, Zn for the electrons. Okay, so this is a statistical phase. It's not a fermion, not a boson, but something in between. Okay? Okay, so that's a basic idea, that you have excitations which have fractional charge and fractional statistics, and they are called anyons. This is a name due to Wilczek and other people. Anyon, which is possible in 2+1 dimension. Okay? So this anion is not a fundamental particle. This anion is a kind of a quasi-particle. The nature of this quasi-particle is not well understood, but nevertheless we can try to make to build up an effective description. Okay. So what is the effective description? Well, the effective description is based on a topological field theory. So now we go from topological effect to topological field theory. And this is the Chern-Simon Lagrangian, Chern-Simon action. Okay? Chern-Simon action is like this. Okay? So A is a gauge field, because you see this is gauge invariant. Okay? And also another important aspect is that it's possible in 3 dimension, because you have this epsilon symbol, which is 3 component, 3 dimension. Okay, and so it is also dominant when you expand the action in terms of small field and small derivative of fields, because the next term is the Maxwell term. Okay, it has more derivatives and also has a mass here. So this is subdominant when you take a small fluctuation around the ground state. And also another interesting aspect is this is not invariant under parity and time reversal. So S going to minus S under parity, P and time reversal. Okay, you can check it. Okay, to discuss parity and time reversal is a lecture, because it's something that very often is not considered, because most of systems are invariant and parity and time reversal. Okay, but roughly speaking, parity is when you have a transformation that is not connected to the identity, and so this is in 3 dimension is, for example, reflection, so x1 and x2, which goes into minus x1, x2. Okay, so that's a parity, and time reversal instead is t, which goes into minus t. That's the time reversal. Okay. So you see that here you have sometimes you have 2 coordinates and 1 time in all pieces, and you see that you will get a minus sign when you do this. Okay. Okay. So is this important that you break a time reversal in parity? Yes, because this system has a magnetic field B, which is not invariant under the same thing. So B goes into minus B when you do parity and time reversal. So this term is a reasonable term. Okay. So now there was I mean, at the same time there was some study from very technical, motivated by technical reason, of anions and Chern-Simon action. So these ideas were around that be used for the quantum Hall effect. let me tell you a couple of things about this action, which fits the physical picture that we discussed before. Okay, so the equation of, so let's suppose that I add some static source. Okay, so I put some current associated to a mu, and so this will be some external sources like test particle. Okay, so for example, the current of a test particle which is sitting in a point. Okay, you put the test particle in somewhere, which could be the quasi-particle there, the quasi-hole. If it is static, then J0 is just the charge. So you put the charge in the fluid at point x0, static. That's going to be the current. Okay. Okay. So what is the, so if I have a discharge, what is the effect of coupling to this Chern-Simons action? Okay. Well, it's very easy. You compute the equation of motion, and the equation of motion is d mu a nu antisymmetrized, which is f mu nu, equal to 2 pi over k epsilon mu nu rho j rho. Okay? Equation of motion. And then if you take a static source, you get that the magnetic field B, so B is in direction orthogonal, okay? So epsilon ij k ij, okay? B is equal to 2 pi over k q. Okay? So if you couple a static charge q to a Chern-Simons field, you get that the field is determined directly from the value of the charge. You see in the Maxwell theory, you will get a different equation. We get d mu f mu nu equal to j nu. Okay, there is a derivative here. This implies that you can have waves. You can have a propagation of photons. So a source can create photons that propagate. Okay, because there is an extra derivative with another derivative inside here. Inside here, you get a D'Alembert equation. So you have waves propagating. Here you don't get this. So this is the field is instantaneously determined by the source. There are no waves. Okay? So in this sense, it is called a topological theory because the topological theory has no local degrees of freedom, propagating local degrees of freedom. Okay? So, no local degrees of freedom, which in this case are photons. Okay? Photons will come if you put this additional term, but we don't put in the low energy limit. We don't consider this. Okay. So what is the effect of this theory? If you have a charge Q, it assigned to it a magnetic field B proportional to Q over kappa. Okay. So basically, a charge Q also become a little solenoid, a little magnetic field. Okay, out of this. Okay? So at this point, it's not difficult to understand that if you put two charges, Q here, another Q here, okay? And you will find that if you bring one around the other, you get an Aharonov-Bohm phase, okay? And the Aharonov-Bohm phase will be again evaluated by this integral of the gauge field, and this will be Q1, Q2, 2 pi over K. So if this particle have fractional statistics, they also have they have a fractional charge, they also have fractional statistics. Okay? Too short? Too fast? I mean, what you can do is you can say, okay, let me solve this equation of motion with two charges, not one, but two. Okay? Repeat the analysis, but if you want to get this, you repeat analysis with another piece. In 2 points, okay, x0 and x0 prime. Oh, x0, x1. Okay? And then you will see that there is a mixed term that gives you this. Okay? So this Chern-Simons theory is basically producing for you the expected properties that I was arguing from the Laughlin theory. Okay? And yes, and yes, and so that could be an effective description of this fluid. So if you have an incompressible fluid, you have a massive phase, okay? But this in this situation is a massive phase of a special kind in which there are these global effects, like the Anion phase, Anion statistics, which make this ground state, this massive phase, a bit special. Okay, that's the idea. Yeah. Okay. Yes. Okay. So that's one property. And then now so what is this small a field? I didn't tell you so far, so we have to clarify this point. Okay. Okay. So let me do a number of steps. Okay. So this small a is not the background field A mu, external field, but it's a kind of dynamical gauge field that you assume that it exists, dynamical in the sense topological, special dynamical. It exists in the theory. The point is that if you have a fluctuation in the fluid somewhere, okay, any kind of fluctuation, it is associated to some conserved current, matter current. And in 2 dimension, in 2 plus 1 dimension, you can represent a conserved current in terms of so-called dual field, like this. Okay? So this is a current of matter fluctuation of small matter fluctuations, okay? But you see that this is conserved, okay? And also you see that this dual field is a gauge field, because if you do okay, this doesn't change, okay? So you say, okay, I have a matter current in 2 plus, for small fluctuation in 2 plus 1 dimension. I can represent by, in this way, by a gauge field, which is a kind of matter gauge field. So that, this is a low energy description, okay? So it's somehow analogous to the Landau theory of critical phenomena, in which you say, I have a center field phi, which is my magnetization, and I write the simplest theory which could describe the breaking of a symmetry. You have a scalar field, the expectation value is the magnetization, then I have a potential that has some minima, and so in some cases these minima produce expectation value of the field phi, in some other it doesn't. Okay, so this field phi is a kind of effective field to describe the low energy physics of your system. In the present case, we are not dealing with the property of spontaneous symmetry breaking. So it's, the physics we are dealing here is a different physics with respect to to spontaneous symmetry breaking. So we don't have scalar fields, okay? But we have a gauge field. Why we have a gauge field? Well, first of all, it's possible to have a gauge field. And this gauge field with such an action has special properties that there are no local excitations and there are anionic phases. So it's a kind of effective field. A is effective gauge field for small matter fluctuations. Okay? So we are going on in this process of guesswork to arrive to write an effective description of this physics of the incompressible fluid. Okay? So it's an educated guesswork that will bring out of some properties, some symmetry, and also anomalies to arrive to a consistent picture for low energy physics. Because we cannot do a microscopic description. So you are, okay? So this is a game that is applied in this case. Okay? Okay, so now we proceed. There is another important aspect that I can couple this current to the external gauge field. So, and the coupling is the usual one. So I have this starting theory, which you can use. No, well, yes. You can use the language of forms, differential forms, because this quantity is, in terms of differential forms, this is A dA, or if you want, A wedge dA. Okay, but let's keep a standard form just not to confuse yourself. Okay, but then this is nothing else that oh, there was missing a 1 over 2 pi here. For convenience, we put a 1 over 2 pi here. So this piece is 1 over 2 pi okay? So this will be the coupling of the matter current to the external background. Okay? And at this point, what we can do, we can integrate out the gauge field, the small a field, okay? And the result is again a Chern-Simon form for the big A, for the external field. How do I get this? Well, this is simply completing a square, because the quadratic theory, integrating out the field, is like taking the extrema of this action. The stream of this action was given, is an equation of motion. You substitute the equation of motion. This is the same as completing the square, okay? And you get this, okay? That maybe you saw. It's a Gaussian integral in a path integral, okay? Gaussian integral, path integral, or if you want, you solve the equation of motion and substitute back, okay? So what is this response action? Response action is, it has the following meaning. I put an extent. I have this incompressible fluid. I suppose that this incompressible fluid describes my system in terms of this effective field a little a, and I put a background, and with the background I perturb the system. I want to see the response of the system. What it does if I put some background, okay? Okay, and so what I will get, the induced current, so is a different current, or response current. So what is the effect of this perturbation by the field A is, by definition, the variation of the action with respect to A mu. Okay, and that this gives 1 over 2 pi k epsilon. Okay, and this is a relativistic form of the Hall current. Okay, because you have that Ji is 1 over 2 pi k epsilon ij ej. So this theory describes a Hall current with a sigma equal to 1 over 2 pi k. So if k is integer and odd, this theory has fractional Hall conductivity of these Laughlin states. Okay? So this is a strong indication that this is a correct theory for the low energy properties of my system. An interesting fact is that this current, as we saw, is a special current. No, that is it involves no dynamics. You see, it's just there is no local dynamics. This is just a global phenomenon. In fact, it is a global phenomenon because you move, as we saw before, we move all the electrons in this spectral flow inside the fluid, but this movement does not really imply any real dynamics. Okay. Okay, and then you say, oh, why k is an integer? Yes, k should be an integer for this quantity to be well defined, for this action to be well defined. In general, that's a property that you can prove. So this must be an integer. It's a coupling constant, but it has to be an integer. Otherwise, this action is not well defined. Yes? Why? Well, that you have to give me half an hour extra time to explain to you. Is gauge invariance. Discussion session, okay? Eh? Let's keep this interesting thing for the discussion session, okay? It's gauge invariance. I mean, gauge invariance not in this case because you have an open boundary. You don't see very well what is gauge invariance. In fact, it will be the topic of next hour. But in more general geometries, this is required for gauge invariance. Okay, so maybe we stop now. Okay, so I mean, I try to support to convince you that this Chern-Simons theory here is the low energy description of these Laughlin states. Okay. Okay, the energy description of the bulk of 2+1 fluid, okay, which has a gap, and so there are no local excitations, but there are these phenomena that there are these global phenomena. One of them is the Hall current, and the other is the fractional statistics. If I consider excitations here, local excitation in static excitation in this bulk. Okay. Now the point. Next step is to understand what is the theory that describes the edge excitations, because in this system, following our understanding of the integer case, which was one body physics, so simple to understand, we figure out that on the boundary there are massless chiral excitations. Okay, so we expect that also in this fractional case, in this fractional case, you also obtain a theory of massless excitations. So also in this case, we are going to somehow guess what the theory is, and relying on properties that from knowledge that we have been developing on massless theories in 1+1 dimensions, so conformal field theories. We have seen that in the case nu equal to 1, you had these chiral fermions, one on one side and one on the other side, and the chiral fermions obey this current algebra. So we define the modes of the current. Okay, modes of the current. In fact, there were two modes for two things for the two branches, okay, in which the field decoupled. And so for any of them, So let me discuss just one of them that I call rho n. We found that there are commutation relation, and also we define the corresponding modes of the energy Hamiltonian. The local Hamiltonian. Okay? No, sorry, I think there was a dagger here, not a dagger. Okay? And this so that so this is the Hamiltonian density. Okay? And so L0 is the Hamiltonian of H. And these obey other relations. Okay? And this number that we said is the central charge, takes the value 1. Okay? Okay? So we characterize this the fermion as one instance of this current algebra. Okay. Now there is a fact that as a theory, as a critical theory, with such properties, with such symmetry properties, and such algebra, is not a single theory, is a family of theories. So there is a critical line. Okay, this critical line is not a critical point as a massless theory, but is a critical line. And this critical line can be parameterized by some parameter kappa, starts from some value, which is different from 0, and goes to infinity. So all theories in this have c equal to 1, and all are fixed points. Maybe you heard about the XY model in statistical mechanics, the one of Rotor. There is a massless phase, which is sometimes called Coulomb phase. And there is a parameter in the Lagrangian that for all these, for all these points in this line, you have a critical phase. Then there is transition to a massive phase, so-called Kosterlitz-Towers transition. So away from this part here, there is a massive phase that we are not interested. Okay. So all theory in this line, they obey the same. They have the same properties. Okay. The same properties. What changes is the eigenvalues, the values that the quantum numbers of this excitation can have. Okay. In particular, this k parameter can be put in relation with the parameter k that I introduced here. Okay. And the value of the excitation you can have is depends on k. So the theory is still massless, but excitations are characterized by different quantum numbers. particular, you have a charge excitation, okay, which will be eigenvalue of a charge, rho naught, this is a charge, and energy, which is, sorry, yes, energy is proportional to L, but so energy excitations is L0 divided 2 pi over L, okay, or if you want 1 over R, and L0 on some charge states is Q square half. Okay, and so in the case of fermion, we had that the charge is integer, okay, and the energy is n square half, 1 over R n square half. This is a part. This is an excitation, okay? So you remember you had this chiral, one chiral branch, okay? The energy of one particle states was k minus, sorry, n was n minus 1/2, okay? And so we filled up to this point. So if I put charge 1, I get 1/2 energy. If I put charge 2, I get 1/2 plus 3/2, okay, and then so on. And so you see that the energy that reproduce here is what you get if you start to put electrons here, excitation, charge excitation on the boundary, okay? Okay? So this was for K equal 1. In general, for general K, the spectrum is different. The spectrum depends on K. It's still a critical line, but the spectrum depends on K. And for general K, you get that the spectrum becomes the possible value of Q are n over K, and the possible value of L0. Okay, let me call this yes, are n square over 2K. So there is an additional K here in general for general case. So in fact, the K in the theory of in this line, K is in fact real. But we are interested in a special value which are integer because we want to describe this. We want to apply this to this theory which has integer value of K, odd value. Okay. Okay. So we do have a theory for edge excitations which has the desired properties for describing excitations, chiral excitation on the boundary. Okay, and because you say, okay, these are kind of quasi-hole, they have this monodromy phase, I can bring them to the boundary. Okay, I can bring this to the boundary, I can bring this to the boundary, and still again I can compute the phase like this, exchange phase, and then and then find the same phase. In fact, you do find the same phase because this correlation function of two of these excitations has a power law behavior. So if let me represent by this two-point function, because it's a scale invariant theory, this quantity should be a power law. Should be a power law, okay? Power law because it's scale invariant, so there is no mass involved, so it's just a power law. Also, the value of this is related to the dimension of this object, because there are no dimension involved in the problem, and these dimensions are given by this quantity L0, and and also there has to be chiral. Uh, so these are complex numbers, okay? So it has to be massless and chiral. Okay? So excitations in this theory will have such a correlator, two-point correlator, and you see that if you bring one around the other, so if you do a rotation of this coordinate here, okay, then you will get a phase, which is what was expected from oh no, sorry, not n but n prime here. What is expected from for the Chern-Simon theory or for the quasi-particle? Okay. So what is this theory? The theory is a theory of a scalar field which is related to a scalar field, which is basically the gauge degrees of freedom that this field reduce on the boundary. So on the boundary, you will find that A mu becomes, no, more precisely, A0 is 0 as a gauge choice, and AI on the boundary becomes di phi. So on the boundary, you have a scalar field. And this scalar field is a theory which realizes these properties of the algebra. Okay? And it's called the chiral boson, or chiral Luttinger liquid. Okay? So let me start to this kind of general idea that is, so in this type of work there is a lot of guesswork, and the guesswork is based on what? It's based on symmetry, on properties, on property of this algebra, math problems, math results that you're going to use, and then convince yourself that this description is valid. Because then you do a number of checks and you see that indeed it works, okay? So, I'm taking much more time than what I expect, but anyhow, it's already too fast. And okay, so let me try to derive for you this bosonic theory. Yes, yes. It's a minimal choice. In fact, there are more general plateaus, well, general filling fraction, which you need more the central charge. In fact, I made a list certain point. This is valid for the Laughlin state, okay? But in fact, there are more general that also you can read in the review I wrote. More general case, for example, 2/5. And or 3/7, okay, or some other number which are observed, and to describe them, you show that this theory is not good enough. So you are forced to change the theory, and the value of the central charge is here, is a numerator, okay. For this, you will live to have more scalar fields, so more copies of the same theory combined in a certain way. Yes. So yes. Yes. That's what I'm going to do. Yes. So Yes, you can do for many fractions. Yes, you can do. You can do for using multi-component bosons. You can do for many fractions. And so the problem is that the problem is opposite. You have too many because the observed value of fractions is very limited. So there are just a couple of series.
But they are not observed for experimental reasons.
For experimental reason, yes.
But in principle, you can accumulate around any real number, many fractions.
No, I mean, for the conformal field theory, effective theory, I could, but for the physics, I have to invent some other. I have to find some other rules that is not possible. In fact, I work on this, and my guiding property is that this incompressible fluid is associated to an extra symmetry. Thank you for that. Very nice, because I can do some very nice question that I can do some advertisement. Okay. So, in fact, the incompressible fluid is associated to a larger symmetry, which is called W infinity symmetry, or also area preserving diffeomorphism. So this is an additional symmetry, because what's the point? The point is that we have seen that the physics of the Landau level depends very much on the magnetic field, on the flux of a magnetic field. So you can deform, and you keep this deformation keeps is a possibility of the incompressible fluid, changing the shape of the fluid. Okay, and you can realize this. All excitation of the incompressible fluid you can analyze as excitation produced by this diffeomorphism of space that preserve the area. Because if preserve the area, preserve magnetic field, preserve the space. Okay? So it's a possible deformation, level by level. Okay? So if you implement this extra symmetry in the algebra here, you get other generators which enlarge the algebra. Okay, and if you work out the property of this more general theory, you find the reason why there are only certain fractional value and not others. Okay, that was my work on double infinity. Okay, okay, basically because no, I don't tell you because it's takes too much. Yes. So also this keep for the discussion session. Okay, so we can derive this theory. It's called the Chiral-Oettinger liquid or chiral boson, and it goes as follows. So we start from the Chern-Simons action. Okay, and then you do kind of a reduction on the boundary. So you take one boundary, okay, and you want to reduce this to a 1 plus 1 dimensional theory on the boundary, okay? And so you have first to put A0 equal to 0, which is a possible gauge choice. And then you have to put AI equal di phi, which is a kind of, it is a gauge disease of freedom, okay? And then this action reduced to a total derivative. And so this becomes, oh sorry, k over 4 pi becomes minus So this is on the manifold, which is a disk d2 times the time r, okay? K over 4 pi integral of over, so d3x, d2x on r, on the boundary S1 cross r of dx phi dt phi, okay? How to prove this? Well, just you just replace thing. Replace, yes. It's a total. You see that it's a total derivative, and then it reduces to this. Okay. There are several more ways to prove this, but this is the simplest. Okay. So that then you say, oh, okay. Uh, It's a boundary term. Okay, boundary term is fine because usually boundary terms you throw away, but in this case there is life on the boundary. So in fact, the boundary requires some extra dynamics because here inside everything is static, but on the boundary you should have these waves, okay, that propagate. Oh, yes. Why? I don't get it. This is a gradient, yes? Why? Why? Because why I'm doing this? There are several explanations, and one explanation is that this is a gauge degrees of freedom, okay, in the bulk, but on the boundary it becomes physical, okay? No, on the boundary, on the boundary. Say, say. Yes. 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 Okay. There are several ways to derive this, and one way is, for example, you solve the equation of motion in the bulk, okay, in absence of sources, okay. That gives you d mu a nu equal to 0, antisymmetric, and the solution is a mu equal to d mu 5. You solve the equation of motion in the bulk, okay. Another possibility is to, so then you say, okay, in the bulk there is nothing, but on the boundary I have some kind of boundary condition to put. And this boundary condition, I have to use this phi that becomes physical, okay? That's so what would be the the kinetic term for this phi? It is inherited from the bulk theory, okay? Another possibility is to say, okay, I have this extra field on the boundary, and the action combined of the boundary and the bulk should be gauge invariant, okay? Because there is conservation of charge between bulk and boundary. And so you can say, okay, this is you put this field, you put this action, and then you do a gauge transformation, and this is not gauge invariant, as you see, it's not gauge invariant, and then you add this piece on the boundary to make it gauge invariant. Okay, so you do an extra gauge transformation. You say, okay, a mu goes into a mu plus d mu lambda, and phi goes into phi plus lambda on the boundary in such a way the combination of bulk and boundary is gauge invariant. That's another possibility. Okay? Okay? Okay, so so this is the plus this condition, this gauge condition on the boundary. So there is anyhow a gauge condition to be put on the boundary. Okay. Okay, so then you say okay, this is a kind of strange theory because you see this is like p q dot. Okay, so there is no Hamiltonian. Well, where is the Hamiltonian? There is no Hamiltonian. Of course, there is no Hamiltonian because this theory, the topological theory, has no Hamiltonian. It's also of this form, PQ dot. You see, there is no Hamiltonian here. It's a topological theory, so no dynamics. So I have to put a dynamics by hand, okay? Because the theory in the bulk was topological. So and then I have to invent a dynamics because I know that the excitation on the boundary are waves. So I have to put a term which is plus or minus, it's the same, no, plus minus h, okay? So it's going to be pq dot minus h of pq, okay? And this is v dx phi square. So it's this is a so-called Luttinger Hamiltonian. Okay, and because this is the current in 1 plus 1 dimension. So it's a j in fact jx is dx phi is represented in this case by field, and so this is a current interaction. But okay, it's also natural to put because it is a scale invariant. You have this velocity of excitation, and you see that the equation of motion will give you dx minus v dt phi dx phi equal to 0. These are the equation of motion. Okay, and so you have this kind of redundant piece, yes, but no, if I put the minus here, I have to put the plus here, yes, yeah, yes, and and so this is a chiral wave. You see, it's a solution of this is phi to phi of solution of this equation of motion are phi of t, which you're not interested, and phi of x minus vt. So it's a chiral wave. Okay? So reducing the theory, the topological theory on the Chern-Simons theory on the boundary, you get a boson with this kind of symplectic structure, and then you add a term which is sensible Hamiltonian to obtain a chiral wave. Okay? Okay, now what you do? You can do canonical quantization because this is a scalar theory. It has a commutation relation. You can expand into modes, and you obtain the spectrum and the property of this theory. The funny thing is that the bosonic theory is able to describe the entire line in terms of this parameter kappa as a quadratic theory in terms of bosonic field. Instead, the fermionic theory we had only works for nu equal to 1, and in general, for nu different from 1 has to be interacting fermions. Interacting fermions that you don't know how to treat. Okay? So that's advantages of 1 plus 1 dimension is so-called bosonization, that you can represent a boson, a fermion in terms of a boson. Sometimes the bosonic description, as in this case, is more powerful because it can describe also interacting fermions. Okay? So if you do canonical quantization of this theory, you are going to reproduce this spectrum of properties. Okay? So I don't do this because it's some work you can find in the review. It's the only interesting fact is that that I want to mention, and is that this field, this boson is special because it's compact. Okay, this is not a normal boson, but because it's a gauge field, so phi is phi plus 2 pi. So it's a compact field. So phi as a function of the coordinate of the boundary that I call x, no? And x is between x is r theta, the angle on the boundary. Okay, so this x going to the boundary here. Okay, is periodic. So phi of x is a periodic function from the boundary to the U1 field, to the U1 group, because it's a gauge, originally was a gauge transformation. Okay? And so this field, when you quantize this field will have waves obeying this equation of motion, but it will also have solitonic modes because of periodicity of the field. And these solitonic modes are again related to the fact that phi is a non-trivial map from a circle to a circle. Okay? Yes? The base is a circle, and the phi is an element of U1 because it's originated from the gauge group. It's a gauge transformation. A is a gauge field. It's a gauge transformation. It's a gauge degrees of freedom of the original Chen-Simon theory. So it can be elevated to an element. It's an element of, if you take a large configuration, it is an element of U1. Not clear? No? What was wrong? So first of all, you accept that the effective theory is a gauge theory. That you accept, right? Because it has a gauge symmetry. Eh? So phi transform with the gauge transformation. So phi itself is an element of the group, and so it's compact. Because an element, a large gauge transformation of phi is u is e to the I phi, and u belongs to U1, is a phase. Not. Don't get your question. We saw this many times. The funny thing is that what was a gauge degrees of freedom on the boundary become a physical degree of freedom, but it remains compact because it was an element of U1. Okay. We keep this for the discussion session. Okay. So let me just say that reproduce these values here. Okay. And also let me just say 2 steps of the derivation. of canonical quantization, it starts from you start from commutation relation, and in the commutation relation that you get from this from the symplectic part there, okay, is going to be commutation relation are going to be relation. So you can work it out. Commutation relation are going to be phi of x dx phi of y equal to 2 pi I over k delta x minus x prime, that x minus y. And then also you expand the field phi of x and t is going to have phi 0 plus minus alpha 0 x minus vt. So let me put v equal to 0 divided by r plus I sum over m alpha m e to the pi m x minus t over L. Okay, so these are waves. These are waves. So this is the wave part, but there is also this part which is still a solution of the equation of motion. You see, a linear and the constant thermal solution, but they have a non-trivial properties that will create a solitonic solution that produce this spectrum here. Okay. So in conclusion, there is yes, please. It's a scalar field, yes. Yes, you want to do canonical quantization, okay? So in the end, you will find that bosonic commutation relations. So canonical quantization is you replace the solution of the equation of motion into the commutator of fields that you got from the Lagrangian, okay? No, these are fields, no? These will become operators. Coefficients become operators, okay? And if you do this, you discover that there are commutation relations between phi 0 and alpha 0 equal to I over k, and alpha n, alpha m equal to n over k delta n plus m 0. Okay? So if you want, you put an at for operators, okay? And okay, so you see that this realized what I was telling you, that this theory realized the first piece of this current algebra for k equal to 1. So for k equal to 1, I can identify the mode of the mode of the current of fermion theory to this mode of this field, okay, this mode here, and including alpha 0. And then there is this additional object that is necessary for making the solitonic modes. Okay, so this canonical quantization of this theory that you can do with some effort produce what you have you had you wanted. So produce this representation of the algebra that with the correct quantum numbers to describe fractional charge and fractional statistics. It is a chiral theory as expected, and it can describe this is the theory that describes the edge the edge of the fractional all states, and also by the anomaly argument you can repeat the anomaly argument in the same way, exactly in the same way as for fermions, because current are expressed now in terms of uh, of the bosonic field and use commutation relation. There is this additional k factor, 1 over k factor, that will produce you a spectral flow of charge 1 over k, not 1, but 1 over k, which is the whole current for fractional Hall effect. Okay, so this is an effective theory that reproduces the anomaly, has an anomaly, is a bosonic theory, but nonetheless has an anomaly, and the anomaly has the same form as the fermion. The only difference that is 1 over k, the k coefficient, basically. But also the dimension has to have the k, this energy and scale dimension have the k dependence. Okay, that's all. Please.
If this lowercase a is U1, so compact gauge field in 2 plus 1 dimensions, how do we know that it's not confined since it's dynamical, or that the dynamics give some confinement?
Confinement is in the Maxwell theory, no? But we don't have Maxwell theory here.
But you still have the irrelevant.
It is a relevant term, but if you have Maxwell plus Chern-Simon, it's a completely different physics. It's so-called topologically massive gauge field, studied by Jacques. I have to mention this is also an important actor of this piece, of this play. It's completely different dynamics, yes, because the Chern-Simon is special. Yes, yes. At this point, yes. At this point, you get a massive photon, and the massive photon is not the Higgs mechanism. It's another mechanism, but in practice, the massive photon. The massive photon creates an anion which is not a point-like, but like a little disk. Okay. So you studied it. If you studied the combined theory, where was it? I cancel. Probably cancel. Okay. Then you will find that the instead of anion, you don't have anions, but you have a kind of little disk of size 1 over m. Okay. Okay. This size, let's say R0, 1 over m. Inside this disk, you have a gauge field, dynamic gauge field with mass, but it decays at distance 1 over m. Okay, and so instead of having you can say you are giving them a size to the quasi-particle if you want. Okay, but for what concern the large distance properties, if you take them apart, then you rotate around one another. It is still the Chern-Simon theory. Okay, okay, and then you can say, oh no, I want to put them together. I want to squeeze them together more than this. So I take a mass which is not too big, but comparable to R0, comparable to the magnetic length. Then you don't get the correct effective theory for so it's not very good. So the good part is when you can take a very large mass. So it's very relevant piece. And yes, please.
The same effect that we studied with the dynamics. derive what they call a Ginsburg-Landau chart sign.
Yes,
They do, they can do dynamics then with that
yes.
model. Is it the same?
No, no. This is the low energy limit of that theory.
Okay.
So it's only. Yes, 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 yes,
Okay.
yes.
Because that is from macroscopic.
Yes, yes, yes. This is effective. Okay. So how do I get? I mean, kind of heuristic argument to get this theory from microscopic. Okay. Well, what do? You say, okay, let me take the path integral. Okay, with fermions in the bulk. Okay. In the bulk, you have okay. Then you put the okay, and then I say, okay, let me put the condition that the current is fixed value. Okay, so I put another field. Well, actually, no, this another field b mu, and then I put okay. Okay, and that makes this makes a Lagrange multiplier that fix the current to some given value. Okay. Okay, so you do the path integral with restrict value of the current, and this current is the fermionic value. Okay, you fix this. Okay, then you do the path integral. And then you can do this Landau-Ginzburg you just said. You integrate out. So what will be the result of this? Okay. The result of this will be in terms of this B field and this J field. This J field you write as I wrote before with an additional thing. Okay. So you parameterize this fixed value of the gauge field in terms of this additional degree of freedom. And then you say, what will be the action in terms of this B field and this A field? That will be the low energy effective theory that you want. Okay? And you start to see that here you have a BA field. Okay? So you start to see that there is a Chen-Simon theory behind. And then you have to either you put in a big computer and you work it out the result, or you start to make guesses. What will be the effective theory after integrate interaction and everything in this fluid phase in which I have a constant density, no excitation in the bulk, and then you start to say, okay, let me invent a term which involves A and B and are the proper symmetry, the minimum number of derivatives, and then you come up with that. You integrate out B and you come up with that. No, because I mean, no, the parameters are left. I mean, from yes, from macroscopic, I check on the experimental value. Okay, from microscopic, in principle, I could compute them, but I cannot do this microscopic derivation. Possibly I can do. Yes, possibly I can do from this Zhang, Anson Zhang, Kivelson work. I can because it's a mixed thing. Okay, I can do this. I can do the calculation, and with some hypothesis, I can do. I can get these values. Also, there is so-called mean field theory. Mean field theory of you can also introduce a sort of mean field theory for the fermion, and then you get to this. Yes, but it's also effective. No, it's a different level of effective theory, not really because microscopically in general is non-perturbative. Okay. Yes. Sorry, we have a.
5 minute break, and then we start with.
So discussion. Thank you. Discussion session is tomorrow.